Hi class. So another component of color that's very useful to learn about is this idea called gamma. Now, let me first highlight the problem. Creating a linear gradient, so in your screen you want to go from black to white and make it nice and smooth in between. This is actually really hard to do. Creating a linear gradient, oops, is hard. And why is it hard? Well, there are two things standing in our way. This is sorry, I should write this out. Going from black to white. Now, there are two things standing in our way. The first is that if we give a linear signal to a display device, okay, we can do that, right? 0%, 10%, 20%, 30%, 40%, 50%, all the way to 100%. We can give a linear signal to a display. The problem is we're going to get nonlinear change in brightness. The displays won't respond linearly. Nonlinear change in brightness. So this is true for LEDs, and it's true for CRTs, and it even changes based on the manufacturer and the style and the technology used in your screens, right? For example, they could compress the dark regions. This is a common problem with old CRTs. The dark regions would be compressed. You couldn't see anything in the black area. You could only see the light things. Everything got too dark. Or it could compress the lighter ones. Where you can see detail in the dark regions, but the light regions are kind of washed out and everything looked kind of white and you couldn't see the detail. That's a common problem I used to have with cheap LCD monitors in the early days. You turn the backlight up and everything's just washed out. You can see all the darkness, but you can't get the detail in the light. So it's non-linear. So that's the first problem. The second problem we have is that even if we can fix that, if we make a device give linear output, so we've solved it. Okay, we've corrected, we get linear output brightness from the monitor. We send it to a person. Oops, I should probably move this. Come on. To the person, well, it turns out that we have nonlinear perception of intensity, okay? So even if you double the intensity, the person might not see it as double the brightness. To make things worse, this is color specific. So we have this problem. In programming, we can make a linear gradient, linear function, but the display device and the reception device, both are highly nonlinear. Okay, so what we do is we have this thing called gamma correction. And really, it's not a topic for this course. This is more of an image processing or signal processing course to get into the depths of how it works. But what gamma correction is we're trying to correct for all this. Attempt to correct and result in a linear gradient. Linear gradient from dark to light, okay? So I'm going to explain most of this using slides. So here's a visual of what I've talked about. We have this idea of an original gradient, but it turns out that, when it's not encoded in a nonlinear fashion, maybe your eyes or the output device, you get this kind of thing happening here. You don't get discernment in the dark regions. Everything just goes to dark, okay? This region here of the pure gradient goes to one chunk. We get most discernment in the middle, and we get compression again at the top. And again, if you've played old video games on a computer where you couldn't get it bright enough, even if it got bright in some regions, you couldn't see the dark, this is a gamma problem, a nonlinear output and perception problem. But what we want to do is go from this linearly encoded to nonlinear correction to get this gamma. So look here, each bin, we can see them, and they're equally distributed. Now, I'm not sure what will come across on your monitor or what will come across through the video, but on my screen I have a color corrected monitor. I can see every band here to the top separately, and they look evenly spaced. So that's the goal. We go from an original idea of linear, we get this funny nonlinear output. We want to correct for that so that the person sees this linear gradient, okay? So the idea behind gamma correction is we take an input, we have a function that takes an input and gives us an output in this corrective function prediction. So you'll see gamma curves look like this, okay? And what this one does is this one decompresses the dark regions. So if I have intensity, at point 0.2, you're actually going to output at 0.5. And what this does is this little region in here that's only 20% of the input, you're going to stretch that to 50% of the output range. And so you're going to stretch it out so it's using more intensity. And then the opposite happens up here. This last 25% of input luminance is going to be compressed to the last 10 or 15% or so here. So it's a nonlinear transform so that some input intensity gets mapped to an output in a nonlinear fashion. So you'll see these gamma curves. They're often, they're called gamma, by the way, because you have this nonlinear function that you use, and gamma is the parameter you modify. It's an exponent in there. You modify it. You can go look it up. It's beyond this course. But you modify this to change the shape of that correction curve. If gamma is 1, it stays linear, so no change. If gamma is bigger than 1, you get these compression of the dark regions and decompression of the light regions. By compression of the dark, again, I mean here, look, I go from 1, 2, 3, 4, 5, so 20%, up to 40% here if the input only maps to 20% of the output. So you get this compression in there. And then you can get a gamma number to specify that curve. Now, if I reduce gamma below 1, you don't want to go negative, it doesn't work. But between 0 and 1, it'll curve in the other direction, the way that we saw in the previous image. Okay. So the idea is you have an image like this, okay, the dark regions are compressed, you can't really see in there. Here's the gamma curve where you really accentuate the bottom and you compress the top, and you meld them together. Hopefully, if it's done perfectly, you aim for this linear reproduction. And here I'll highlight that you can see the dark regions, you can discern them, but the bright regions here aren't washed out either. So this gamma is a nonlinear correction to really bring out the shadows without compressing the top, okay? There's a last couple here. So here's an example of an image. The original is gamma of 1. This probably shouldn't be there. Gamma of 1, and as you increase the gamma, you're compressing the dark region, decompressing the dark. Yeah, no wonder I got confused. I'm decreasing the gamma, but less than 1. As I decrease the gamma, I'm uncompressing the dark regions and getting all my detail out. But you'll notice what will happen is we're losing the detail in the dress here in the white. You can't really see all the little features. Look in the original, the water and the dress have all these little features you can see. In the bottom here, they're kind of washed out. And then if we go in the other direction, gamma of 1 and gamma of 2, then it just gets darker. But now you can really see the detail in those light regions, and the rest is all gone. So gamma is very popular in image processing because you can emphasize what you want the machine to see by how you use gamma. Okay, so that's gamma correction. That's all I'm really going to talk about it. You will come across it. A lot of video games offer it. You can modify it in your computer. Now you have an idea of what this means. We're just trying to correct for nonlinear output and perception and give a linear perception curve.